So here's a post that showed up on r/learnmath the other day. I thought it was kind of interesting. It's titled Termination versus Irrationality. So we've got someone here asking about the definition of irrational numbers. Let's read through their post real quick. They say, why do we classify numbers as rational versus irrational rather than by whether their base 10 expansion terminates? Suppose we fixed base 10 and classified numbers as terminating versus non-terminating. What would we lose or have to change mathematically? Like, hypothetically, what difference will it make? I know termination depends on the base, but what if we fix a base, say base 10? Guess what I am asking is, why do we care so much about ratios and rationality when we can have other ways to classify numbers? So there's a couple points of this question that I think are a little bit confused. Perhaps the most important one is that they're trying to say irrational numbers, which are numbers that cannot be written as a ratio of integers, those are the same as base 10 numbers whose decimal expansions don't terminate. But I assume just due to carelessness, they've missed the fact that that's not quite true. Of course, you have fractions like 1/7 and 1/9 and 1/11, where their decimal expansions never terminate. They are infinite repeating decimal expansions, and obviously those are rational numbers. So what the OP means to draw here is this equivalence between irrational number and decimal expansions that neither repeat nor terminate. So why do we typically define rational numbers as, we can't express it as a ratio of integers? Why do we do that instead of focusing in on the base 10 decimal expansion, which never terminates or repeats? And that's a fine question. You can see that the vote counter on the Reddit thread is at 0, which means they've been downvoted, which I notice a lot on math subreddits. It's just a little funny on these communities like r/learnmath that seems explicitly oriented towards people learning mathematics, and yet people ask questions that, if you wanted to be a little bit nasty, you could say that's a silly question, and they get downvoted. Where are they? Aren't they at r/learnmath, not r/nomath? I won't be too critical. I make fun of people sometimes too, but this is the r/learnmath subreddit. Come on. So let's go quick here and answer the rest of their questions, and then we'll look at some of the other people's responses to this interesting thread. So they said, suppose we fix base 10 and classified numbers as terminating versus non-terminating. Like we said, we'll just give them the grace of adjusting their definition so that it actually works as just a different way to characterize irrational numbers. So we're talking about terminating and repeating, or terminating or repeating, versus non-terminating and non-repeating. So the rational versus irrational. What would we lose or have to change mathematically? Of course, the point of definitions here is that you don't lose anything. They're equivalent. And sometimes, in different contexts, different definitions are preferred. There's usually a standard, historically speaking, there's usually a standard definition, and often that's going to be not just the historical standard, but also the one that's most common to encounter in any context whatsoever. But as you get into more complicated areas of mathematics, there are reasons you might want to use any number of equivalent characterizations of a concept. And oftentimes, the first thing you do once you learn a new definition in mathematics is to prove some equivalent characterizations. A classic example that comes to my mind is bipartite graphs and graphs that have no odd cycles. Sometimes if you're talking about bipartite graphs, you want to use kind of that OG definition that you can separate the vertices into two disjoint sets so that every edge goes between the sets. But sometimes it's most important to focus on the lack of an odd cycle that exists within all bipartite graphs and which also characterizes them. So just by the virtue of this being an alternative definition, which OP is trying to understand, maybe OP likes this definition better, why doesn't everybody else just use this definition? Why do we focus so much on this ratio thing? What would we lose if we didn't? We wouldn't lose anything. That's the great thing about having these equivalent definitions. And then I think they really answer the crux of their own question in the last couple sentences here. I know termination depends on the base, so right there is a huge reason to prefer the ratio-centric definition of rational numbers. It makes a lot less sense to define a mathematical concept using something that's base dependent. If you have to fix the base, then it becomes clear that you're not actually capturing something that's inherent to the quantity. It's not inherent to the quantity, it's inherent to the quantity when expressed using this base. And with the definition, that's probably not exactly what we're trying to use as the go-to standard definition, something that depends on what base you're in. And of course, although it is true that termination depends on the base, 1/3 in base 10 does not terminate, but 1/3 in base 12 is 0.4, so terminates very quickly. What the OP actually intended to focus on is totally base independent. So a rational number, it might terminate, and that will depend on the base, but it also might just repeat. Of course, you can wrap this all into just repeating if we regard a terminating decimal to repeat zeros forever afterwards. But either way, a rational number is always going to terminate or repeat in any base. So that actually is base independent. It doesn't depend on the base at all. If it's rational, it's either going to terminate or repeat in any single base. So you don't have to fix base 10 to capture that distinction. It's always going to be the irrational numbers which do not repeat and do not terminate. The last question's a little strange. They say, guess what I am asking is, why do we care so much about ratios and rationality when we can have other ways to classify numbers? And I'm not 100% sure of the intention of that question, just reading it on the surface. Yeah, we have other ways to classify numbers, and we classify them in other ways all the time. You got even numbers, you got numbers that are congruent to 1 mod 4, you've got prime numbers, you got perfect numbers, you got Fermat numbers. There's all sorts of different ways to classify numbers. Rational and irrational is a pretty darn important one. But yeah, I mean, we do classify them in all sorts of other ways. I suppose what they're actually trying to get at is, when it comes to the discussion of rational and irrational, why is the focus so much on ratio? And that question, too, does sound a little bit silly, because obviously ratio is the word there. It's the operating word. Rationality, it's a ratio. So yeah, ratio is the crux of this whole thing. It's the crux of the idea. It's incommensurable quantities, as the Greeks would have called it. It is the historical fundamental definition, is these ratios of numbers that actually can't be found. You can't find a perfect ratio for your classic irrational numbers like √2 and pi and the uncountably infinitely many others which we choose not to name. Anyways, long story short, be careful with these definitions. It's not the case that rational numbers will always have a terminating decimal expansion. Sometimes they repeat. But irrational numbers in any base, they're never going to terminate and they're never going to repeat when you write out their base whatever expansion. So if you would like, you can define them based on how their expansions behave in whatever base you fancy talking about. There's something that feels a little bit lost in that definition, though. You're losing the simplistic focus on just a ratio of numbers that doesn't exist. And I think there's something very beautiful and simple about the standard definition of rational numbers. However, in certain contexts, it may be preferable to speak about the decimal expansion definition. There's plenty of times when you're talking to a group of students and they're trying to do stuff on their calculators or writing out numbers, and you say, oh, this is an irrational number. So what you've written down from your calculator is actually an approximation. The decimal doesn't repeat and it doesn't terminate. The calculator's just given you the first 10 digits. In a context like that, it makes sense to focus on the decimal expansion. You'd hope the student knows the actual definition of irrational number, or at least has heard it in the past, even if he couldn't recall it. But, depending on the context, the decimal expansion definition makes sense to focus on. Take a quick look at some of the replies here. The first one was, rational numbers are closed under multiplication and division. If you take two rational numbers and multiply or divide them, you get a rational number out. The same is not necessarily true for terminating numbers. 1 and 3 are both terminating, but 1/3 is not. OP says that makes sense, but this comment misses the point, doesn't it? This comment misses the point because it's not addressing the fact that OP's definition has a slight error. It is the case that rational numbers are closed under multiplication and division, but if we assume, and that terminating numbers are not, but if we assume that what OP meant was terminating or repeating, as in the rational numbers and how their decimal expansions behave, those are closed under multiplication and division. The point being, you can't multiply or divide two rational numbers and get an irrational number. So this comment is like, it's playing on an error of OP's, but without actually pointing it out. So, I mean, that kind of misses the point. Here's another one. A number is rational if it can be written as a fraction of two integers. It has nothing to do with bases. The set of rational numbers is the same regardless of which base you use to represent them. Yep, that doesn't really address the question at all. That's just a statement of the definition. The closest we get to addressing anything here is saying it has nothing to do with bases. So the OP wanting to fix a base and focus on the expansion in that base, you know, maybe that misses the point a little bit. This other comment actually addresses the error that OP made. It's not just terminating versus non-terminating, it's terminating, non-terminating, and repeating. And they say repeating and terminating depends on the base, but both are rational. Exactly. Rational versus irrational is the more fundamental idea. Well, rational versus irrational is what we're talking about one way or another. It's just the matter of how we choose to characterize it. But yeah, it doesn't depend on any characteristic of one particular representation. So to focus on one particular representation, like a base 10 representation, to define the numbers, it's a fine way to do it, but it would be a weird standard. Someone else points out you seem to have omitted repeating decimals from your post, and OP says that's what made me wonder about this in the first place. I realized that at least in the base 10 system, you cannot reliably find an exact value for a repeating non-terminating decimal, even if it's rational. I'm not sure what they mean by that. Other people go on to point out you certainly can find the exact value. I mean, the decimal expansion is the exact value, even if it is repeating. And if you want to find the fraction that it converges to or that it equals, you just use infinite series. So unless they're getting into some ultra finitist stuff here, I think OP's just a little bit confused with just the whole decimal thing in general. It can be a little confusing once you get to these infinite decimals and repeating decimals. After looking at some more of OP's comments, it seems like their big issue might just be, why do we care so much about rational versus irrational numbers? And we could go on and talk about that at length, but to put it simply, in many respects, they're very different creatures. And if you just read the first chapter, or it might often even be like chapter 0 of most any real analysis book, you will understand the great difference between the rationals and the irrationals, and how there is some trouble, trickery, and a great depth of mathematical maturity and mathematical development in history, which had to be brought to bear to unionize those two sets to grant us a rigorous foundation for our real numbers. So they're very different types of numbers, and the classic standard definition, which is all about the ratios, is a beautiful, simple thing. There's no need to sully it with decimal expansions.